So we're going to briefly cover the concept called elasticity. You can think of something like elastic, a rubber band, an elastic band. I know if I have a rubber band, I can stretch it out, assuming I don't break it. If I pull outwards on it, it gets longer. When I let go, it snaps back to its original shape. We call this elastic behavior when an object, after it has experienced some sort of forces and pressure differences, that it snaps back to its original shape. Now, some materials change length better than others or change shape better than others, and some materials don't change shape much at all before they break. Ultimately, to test for elasticity, we would need a machine that applies some sort of what we call stress. Not our everyday usage, of course, of the use of the word stress. The physics definition of stress is some sort of force applied over a cross-sectional area. So it's a pressure, essentially. So the rubber band, for example, we're applying the force. The cross-sectional area would be cutting that little rubber band, looking at its tiny little cross-sectional area. That's what we're talking about, is the forces that we're applying that over. We measure that stress and compare it to what is called the strain. The strain is a measure of how the object's shape changes. In the case of a rubber band, we make it longer. We change its length. So L naught would represent the original length. Delta L is how much it lengthens by. So it'd be the new length minus the original length. So essentially, it's just the change in length. If we were to measure this and set up a system, we would get a very shallow line for a rubber band. And that's because it doesn't take a whole lot of force per area, a whole lot of stress, to get a pretty decent change in length. So the force per area applied, it doesn't need to be very large to get a fairly decent change in length, which when we take delta L over the original length, we still get a fairly decent comparable value. If we took something else, so for example, when I was in grad school, I did material testing on bone. And I got these graphs. Mine wasn't pulling on bone, it was compressing. So I had little cylinders of bone and a machine that pushed into the bone. So a small force per area resulted in a very small strain. And so ultimately, it takes a really large stress to get a strain. That the slope of that line is very steep compared to the slope of the line for a rubber band. As long as that slope stays constant, we say the material is behaving elastically. Meaning if we released the stress, we released the pressure, the material would go back to its original shape. Now, granted, there is always a certain amount of stress that will make the object break or fail. So, for example, going back to this concept of bone, it would be a straight line and then suddenly you would see a jagged line. It's once at this point that the material fails, essentially. It breaks. It no longer behaves elastically. and so it won't go back to its original shape. All materials have a specific slope that represents how that material behaves. The slope of this stress over strain graph is called the elastic modulus. There's different types of elastic modulus. We only look at two. One of them is called Young's modulus. And this modulus, this is essentially what I'm representing here. You apply tension or compression, so some sort of force per area along a line. So you're either making it longer, the object longer, or shorter. So you're not changing volume, you're not twisting it in any way, you're only applying forces along the length of the object, which ultimately only makes the object longer or shorter. So what we end up with is, if I kind of rearrange this, I can say the stress applied is equal to what we call the Young's modulus, so we use a capital Y to represent that, times the strain. But the stress is the force per area that is being applied to this material. So like an elastic band, it's the force being applied along the length that's making the elastic band get longer. That will equal the Young's modulus for that particular material times the delta L over L naught, which represents the strain. Why Young's modulus is unique to the material. So for example, let me jump over here to the test notes. Oops. We have a table in here that has, so this is on page 3 of our test notes. This table has some different Young's moduli values. These are just values that were in the book. So aluminum, for example, Young's modulus, 7 times 10 to the 10th newtons per meter squared. That's unique to aluminum. So every material has its own unique Young's modulus, which in turn tells you how the material will deform, change length, based on the stress, the force per area applied. Not all materials, I saw concrete listed on there. That's not a full picture for concrete, because concrete, it's probably the value for compression specifically, would be my assumption, because concrete does not handle tension very well. Meaning, if we have a piece of concrete and set up some sort of machine to try to stretch it out, it fails very quickly. It does not withstand forces and pressures trying to pull it longer, which is why we have reinforced concrete, is to maintain and capitalize on the ability of the concrete to be strong in compression. You do not need to worry about whether it's the same for tension or compression. Ultimately, Young's modulus, we just need to keep in mind it's specific to tension and compression along a line. So if something's going to get longer or shorter, we can jump to Young's modulus and relate that to the forces that are applied. We'll do an example. Well, I'll do the example now. Let me go find it. Okay, so here is a problem. We have a 0.5 meter long guitar string. It has a cross-sectional area of 1 × 10⁻⁶ meters squared. It has a Young's modulus of 2 × 10⁹ newtons per meter squared. By how much must you stretch the string to obtain a tension of 20 newtons? Okay, so our L naught, our original length is 0.5 meters. The area, they've already calculated for us, so 1 × 10⁻⁶ meters squared. Young's modulus, so whatever the material is that makes up this string gives it a Young's modulus of 2 × 10⁹. We're trying to figure out how much you need to stretch the string. So delta L. What does delta L need to be for the tension within the string to be 20 newtons? So essentially, we want the force in the string to be 20 newtons. Since we are just stretching the string, we're making it longer, that's why we want to work with Young's modulus. So the stress, the force per area, is equal to Young's modulus times the strain, which is delta L, over L naught. Looking for delta L, we can bring L naught over, we can bring Y over, and leaves us with delta L. So we want the force to be 20 newtons. The original length is 0.5 meter. The area in meters squared, and Young's modulus in newtons per meter squared. So the meter squareds are canceling right here. The newtons are canceling. That's leaving us with meters as our answer. So 20. 5, oops. X, 6. So 0.005 meters. We're stretching this string by 5 millimeters in order to get this tension of 20 newtons. For those that play musical instruments, we tighten the string or loosen the string to get it to play the note we want. That note we want directly correlates to a specific tension in the string. But here, ultimately, Young's modulus equation, partially because they give us Young's modulus, but also because we're just making the string longer, we're stretching it out a little bit. And so Young's modulus, notice the units are newtons per meter squared for the Young's modulus, just like the stress. And that's because the strain, the delta L over L, has no units. Okay, one other modulus that we cover is called the bulk modulus. And this is related to changing volume. So somehow we're changing the volume overall. When we say that the stress is going to be equal to this bulk modulus, which we're going to call capital B, times the strain, stress is still force per area, but the stress has to be some sort of change. Since we're talking three-dimensionally, we tend to call this a change in pressure, because either we've got to increase the pressure from all sides, so like a trash compactor. Do they even make those anymore? So you have a container you can put your trash in, and then the machine compresses it into a smaller location. And so the pressure, the trash is getting pushed in on all sides. And so that's why we call it a change in pressure as opposed to just the force per area, because all three sides of the material are getting pressed upon. The strain ends up being delta V over V naught. So we're looking at how the volume overall is changing. Now, when you see this equation, you're going to see a negative sign. The reason for the negative sign is to make the bulk modulus positive. If delta P is positive, meaning we're increasing the pressure on something, then that's going to make delta V negative because the material will fit into a smaller space. The final volume will be smaller than the initial volume. And the opposite is true. If delta P is negative, meaning the pressure got smaller, then delta V will be positive. The object will expand. And so that's why there's the negative sign in the equation, is just to balance out the fact that delta P and delta V are always opposite in sign. Any problems you see along these lines will be pretty basic. You get to take, well, depending upon what degree you're planning on studying, you may very well get to take the material science classes, the strengths of materials, that sort of thing, where you'll dive a lot deeper into these concepts. So we're just giving you a brief introduction.